Hello, and thank you for giving me the opportunity to give my talk here today. So I'm going to talk about the development of a low-cost ventilator prototype. This was a project initiated by myself in March or April 2020. We know that there was the corona crisis in Europe kind of exploding, and all the governments were buying and ordering medical equipment like ventilators or face masks. And looked it up in the internet at that time. You probably could find hundreds and thousands of do-it-yourself ventilators done by some students or so. And there was also lots of challenges, but one particular challenge, which is the Code Life Ventilator Challenge, sponsored by Montreal General Hospital Foundation and McGill University. And they wanted to they wanted to see all the projects of people all over the world. Unfortunately, I couldn't participate there because the deadline expired already, but this was a very crucial moment for me finding out about this challenge, because they very carefully and specifically formulated a document where they wrote down requirements for the ventilator. So these are only some, of course, but these are some requirements that a ventilator has to fulfill if it should be used for treating COVID-19 patients. And if you want, so you can group these requirements into three subgroups. The availability issue, because this kind of produced the problem that there are very special components that are not available on the market anymore if everyone buys ventilators. It should use off-the-shelf components. The safety issue, it should be, of course, robust. It should run at least for 14 days for 100% duty cycle. And it should also cope with oxygen atmosphere, which is very corrosive. And the third one, of course, it's necessary that the functionality is that is functional, that it works proper, and that the certain parameters can be adjusted. So they also wrote about pressure controlled ventilation, which means that that you have a lung which is basically connected in the inhalation phase to a inspiratory pressure, a high pressure, and in the exhalation phase, which is here in blue, to a lower pressure. This P value is post and expiratory pressure. So you basically inflate the lung with a higher pressure and then deflate it against a lower pressure, but this low pressure is still higher than the surrounding pressure, the atmosphere. So here you can, so this is basically done in a very simple way by just connecting the lung to these pressure lines and switch them through. So I thought about how to get some adjustable inspiratory pressure, and what part can I use to fulfill these requirements, because each subcomponent of the ventilator, of course, also has to fulfill these requirements like availability, safety, and functionality. And this is me. I'm a scuba diver, and I thought about using a diving regulator for this purpose, for regulating the pressure, the inspiratory pressure. So you have the availability. It's an off-the-shelf component. You have the you have the safety because it's certified for breathing applications already, and also it's certified for oxygen atmospheres because nitrogen, for example, nitrox is a gas mixture that you breathe as a diver if you go deeper or if you want to dive longer. And this is a gas mixture that is also enriched with oxygen. And in the European Union, there's a regulation that whenever some component uses an oxygen-enriched air, then it must also be safe for 100% oxygen. So this is also checked. And of course, it has the functionality. It is a pressure regulator and nothing else. So how would this work? This is the scuba diving regulator. It takes high pressure, like 10 bars or so, and by a valve transforms it into a surrounding pressure. So basically down here, there's a membrane, and this membrane actuates up on the valve and does this trick. So we actually need here inspiratory pressure up to 40 millibars. And so how can we adjust the pressure here, the surrounding pressure? Well, we just put the scuba diving regulator in its natural environment, which is water. So we put it in this column, in this water column, and fill it up. And the static pressure of 40 centimeter water column is 40 millibars. So we can fill it up with water. And so in this hose, we just have 40 millibars. So by using this, we manufactured a prototype, which looks like this. Here is the water column again, and all the other parts. I think it's better to explain them with a schematic because out of these pictures, it's not very obvious what is what. So here's the ventilator concept. We use the Raspberry Pi and electronic and some connection boards and an LCD display to control the whole system. And you can see this is the ventilator and everything else is the surroundings. So we have here the media, a connection that pressurized air or air and oxygen, and here the patient and ambient air. And you can see, if you remember the picture from before, you have here the red line, which is the line where where the inspiratory pressure is, and here a line where the post and expiratory pressure is. So here's the valve, which switches from here to here, and which is connected to the patient. So now I go through the components. This pressure regulator, as I told you before, is adjustable. So we have to adjust the water level of this water tank. And this is done by a separate water tank, which is on this lifting mechanism. And by coupling this water tank on this lifting mechanism and this water tank, we can create these coupling vessels. And if you lift the water tank up and down, you can also lift the water level up and down. So by this, you can adjust the pressure regulated. We also have here afterwards the humidifier. Out of this pressure regulator, there's air coming out of this pressure regulator, but this air is, of course, very dry. So we have to humidify this by letting it through a glass bottle. and filled with water. And this air bubbles through the water and then gets humidified. You also need to heat it because of the vaporization enthalpy. And you want to heat this up to 37 or 36 degrees or something to apply warm and humid air to the patient. Also, whenever you do something, whenever you have an actuator, you also want to sense something. So we have here an oxygen sensor, which is just this part that we attach to it. It's just bought oxygen sensor. And these 4 locations where at each location are again 3 sensors which measure pressure, temperature, and humidity each. So we have 3 times the same values at each location, and this redundancy is used for getting error correction. So we can say, well, take the median of those 3 sensors, and if one is going to die, one sensor, then the other 2 still have valid sensor values, and therefore we can take the median and it's still working. And at the same time, we can set an alarm to tell someone to replace the whole module, which is just plug it out and plug the new one in. So the next part here is the 3-2 valve. It's just a clamped valve. So these hoses are just clamped, either the upper or the lower one, and thereby letting air out to the patient. The next component is the flow sensor. This was also a part that is originally from another industry. So it's from the automotive industry. It's just a air mass sensor, which is used for cars, for the motor, for the air that is flowing into the motor. And this, of course, the cars, they need much more air, but by reducing the diameter here, you can increase the velocity of the flow here, and thereby getting down to airflow, to sensing airflows that are so it's capable to sense airflows that are much less than in cars. So here is a dehumidifier and a CO2 sensor. The CO2 sensor is an optical sensor which is working on the principle of a non-dispersive infrared. And of course, if this is optical, then it's very prone to errors if it is condensing. So we need a dehumidifier to get out the humidity and condense this down. And then, so it's condensed here. Here is a Peltier cooler, and then the cold air comes out here and is heated again, so that the relative humidity sinks down to a level below 100%. And then it's going to the CO2 sensor. So now I want to show just a small video about the first, let's say, test. I have a test lung here. It's just a bottle of, it's just a 5-liter bottle. And you can see how it is inflated and deflated. You can also get the notion of the pressure curves I showed you before on the LCD screen. So you see that the bottle is inflated and exflated, and you see also the pressure curves wandering from left to the right picture. So I've talked about a low-cost ventilator concept. So now we have to, I just want to show a slide about the costs. We have here, I have subdivided the costs into some subsections. The greatest parts are the pneumatics and the sensors. So these cost a bit more than 1,000 euros. And all in all, it's 1,700 euros as it stands there, as you saw in the picture. So to my conclusion, I built a prototype using these high quality off-the-shelf components. And I think the principle was proven here. Of course, it's also cheap and good available for, especially for poor countries. I think it's a good thing that they can build their own cheap and maybe probably proper working equipment if they cannot afford a lot of ventilators. So what is the next steps? I want to publish all the details and the code and the construction manual to offer it to anybody, and then do some optimization design, especially on the flow meter and the capnography. So last but not least, I want to thank Robert Holzinger, who programmed the Raspberry Pi, and also my sister Martina and her husband Christian, who also did, for example, the construction work, the CAD construction or the CAD design for the water column vessel. So thank you for giving me the opportunity to talk here.